thanks a lot, the organizer, to enable me to speak about these biomarkers in polarization spectra of planet Earth. This is more an astronomical now, coming back to the astrophysical side of detecting biomarkers. I'm with the European Southern Observatory, so I'm an astronomer, actually at this amazing site in Paranal, and many things come together there. What you see is the billion of stars of our galaxy in the galactic center. So just to remind you, each of these stars holds at least one planet, okay? The other thing, what comes together here is this amazing site in the north of Chile, a perfect observation site and perfectly, I think, put together with this amazing observatory, high-tech pure. And the other thing that is extremely important when to make progress in this field is actually that we are not now only astronomers who do this, but we need the help actually of metrologists. So I'm happy that Claudia and Michael, her student now from the Metrology Institute, have teamed up, because they, as you will see, are essential for modeling. And we do need, I mean, to understand the Earth atmosphere, we do need the latest 3D vector radiative transfer models of the Earth that only the metrologists actually have at this point. So no astrobiology conference without Carl Sagan, which was happily cited just now, but also these iconic images of the Voyager lookbacks that everyone, I hope, knows. I hope also the young students know them. These are lookback of Voyager probe flying out of the solar system to the planets of the solar system. But it exemplifies very well, I think, the problem, or one of the problems we have if we are looking for the question for biosignatures, biomarkers, inhabited planets. Only one, of course, of these specks of lights holds life, right? And sometimes they do the quiz, but I don't need to do it. You all know which one. So this is the summary slide I have prepared, but this is also a guide through the talk a little bit. So what can spectropolarimetry, now as very specific techniques of planet Earth, tell us and allows us? Well, it constrains the surface properties, the atmosphere and the cloud properties. So this is a set of properties of planet Earth. We can discriminate ocean, land and vegetated surfaces when we observe planet Earth like this. We see the Sun-Glint, the polarized Sun-Glint reflected on water. We can very well characterize oxygen and possibly ozone. And yes, of course, we study Earth as a template for exo-Earths. So what are polarimetric signatures that we all know about when we are in our daily life on Earth? So one is certainly the rainbow feature. As you know, the rainbow is heavily polarized in the other perpendicular direction. You would not see the scattered signal of the rainbow droplets. You see the same effect, by the way, when you look from space towards the Earth, and you see what this is called cloud bow. So you see in the right scattering geometry, you do see the rainbows, which now imprint as real cloud bows. So this has been observed by a satellite. And you see other things. So this is another satellite observation of the Earth's surface. These are typically weather or climate satellites that look on Earth at small patches and that are concurrently observing everything. What you see here, it's very sensitive to this glint, the polarized glint, that Brewster angle. It's not so sensitive to actually the land surfaces in this case, but it's also sensitive to some of the cloud structures. So polarimetric signatures of planet Earth as a tool to study Earth and to see imprints eventually also, and to apply these techniques on exoplanets is not new. So there has been work done before. And just to remind you what are the main factors that influence these polarimetric signatures, it's first of all, okay, what you see here is the phase angle and the polarization degree. Now this should be 100%, this is 0%. So all these curves just tell you that the degree of polarization is heavily dependent on the phase angle, as you can imagine from a Rayleigh atmosphere. Rayleigh scatterer would peak at 90 degrees. I hope it does. Well, these are days from something, so this is a 90-degree phase angle geometry. So where you have maximum polarization and minimum polarization, either in forward or in backward scattering. You see also that there is a difference of the expected polarization depending on the surface albedo. If you have an ocean surface or a land surface, this deviates quite significantly in albedo. The ocean is typically black and land is not so black. So if it's a black surface, you see the full effect of the atmosphere, while if there's a white surface, you have some depolarization. And even more, you see the impact again of clouds versus no clouds. So clouds add to albedo. Clouds are white, so they typically reduce the effect of polarization that you would expect to see. And I would also like to point out that these first measurements of the Earth polarization were done by the French astronomer Dollfus, and his data points were used or can be used to actually match the models. He was a very smart observer. So what do we want to do in this experiment? So we want to observe Earth in a way like the Voyager flyby from somewhere outside the Earth, like here from the moon. So and not like a satellite where we only peek down to a very specific area, but we want to catch the global properties of the polarization spectra. So as we are poor people, we cannot build a observatory on the moon. So, but what we use instead is we use the moon as a mirror to observe the Earth. So how is that? So this is the observatory. And we look at the moon, and actually at this part of the moon, which is not directly illuminated by the sun, and yes, we use it as a mirror. So this is called Earthshine, and this is a very well-known technique, well, not as techniques, but it's well-known that actually the non-illuminated side of the moon contains information, the information of the Earth's property. And this has been written up by actually Leonardo da Vinci already more than 500 years ago in his Codex Leicester. So in practice, what to know? So this is the sun. This is the object. This is the scatterer. What we use. So sun is shining, reflected on the moon, and we are observing the moon just as a mirror. So maybe this animation works. I don't know. So you have the photons. Here is the effect that we want to study, the scattering effect at the Earth's surface, and here's the reflection effect, and here's our observatory where we observe this. Okay, so we observe this part of the Earth by sitting there. One very important message here. So these Earthshine observations are old. They have been done in the 80s and in the 90s in terms of spectroscopy. The modulation of the signal, or the research, the signal comes from the scattering event. If you do just spectroscopy, you would have another effect of the Earth's atmosphere on the intensity signal. While we are doing polarization, we are catching the effects here, but we are not impacted by the second effect of the transmission spectrum, because the polarization spectra are not altered through transmission. So this is a big benefit in using polarization in interpreting these data. This is much simpler in a sense. Oops, okay. So what you can do here, or what we did some years ago, we observed the Earth in two different phases, and I apologize why these images are not nice, but what it should show is that these are two different phases actually of the Earth that show two different surface and cloud structures. both at a similar quadrature phase, so where you expect a high polarization signal, but the ocean fraction, so you don't see it here. This is the Atlantic side of the Earth, while this is the Pacific side. So the Pacific side contains much more ocean fraction, while the cloud fraction in this part was higher than in this part. And you also have some differences in the vegetated areas that are seen at this aspect. So here's Europe, Africa, while here's the Pacific, and it's still true that Europe and Africa hold some vegetated area, despite other claims. These are the results. What's shown here is spectra, wavelength versus the degree of polarization, wavelength versus the d of polarization at these two distinct epochs. The measurements are actually the red line, okay? So you do see that in the continuum and in the absolute values, actually one epoch it has a higher polarization. You do see also these black lines, which are various models that were available at the time being. So these models actually, they fit quite well in the blue part, in the Rayleigh part of the spectrum. So they are very good here. But as you can also see here, they fail miserably to explain the red part of the spectrum just in the continuum, because they predict a much too low polarization, degree of polarization than that was measured. So this is good and bad. Still, what you can do is you can now zoom in, so assume a pseudo continuum and see what is on top of this continuum, what are the residuals, and these are the red lines, again with some models. The red lines and with some models. The green line is just gives a proxy of the accuracy of the measurements, and that's the scale here. So this is a scale of percent, and actually the precision of these measurements is much below a per mil, 0.1 per mil actually per wavelength bin. So this is quite an accurate measurement, and all these features that you see here are not spurious, they are real. And as you can also see, the same models that describe the blue and fail in the red, however, they also can sort of explain the residuals, and in particular, two features. One is the oxygen strength that we see in polarization, in emission, that's the oxygen A band. And another feature is actually here is what is called the vegetation red edge, or the imprint in the differential vegetation index, that is clearly distinct in both measurements. So this is good and bad news in a way. So we recover all the main features that we expect from this experiment. However, we miserably fail to explain the physics of these spectra. Nevertheless, we were happy that nature accepted this, so we were unable to explain maybe most of this, but good enough for nature. It took us now more than 5 years to better explain what's happening here, and what type of models are needed to really explain these spectra. Now the two images are in better quality. So again, these April and June 2011 aspects of Earth with their clouds and with their aspects. So we just published this work, mainly driven by the meteorologists because of their models, and it's the influence of aerosols, clouds, and the Sun-Glint actually that tends to explain the red excess, or the red color of these polarization spectra. It's a little bit more complicated than this. But the high clouds and the treatment of the high clouds, of the ice clouds, of the cirrus clouds is extremely important, extremely sensitive. And this is interesting because we get a handle on the sensitivity of our parameters. So what is sensitive? So I would also just to point out that we see the Sun-Glint in our spectra, and it contributes. So these are again the two aspect ratios. These are how you would expect the Sun-Glint with a reflecting ocean surface. But remember, only here we had the ocean surface, and here we did not see the glint because this was Africa. And so we do see here the effect of the Sun-Glint a little bit diluted by the cloud patterns. And the Sun-Glint is a very active detecting of glints in general is a very active area. So a series of papers on Earth and on exoplanet applications, satellites are looking for this signature. And I also would like to point out and advertise the poster B2 by Kim Bott, who nicely also captures many of the properties of the polarized spectra of planets and of Earth, including the glint. Going further here is what is left to do. So what you see here again are more measurements of the Earthshine spectra. And now these are the continuums. These are now the zooms in the oxygen A band. And as you can see here in different epochs, this is highly variable. By the way, this is not noise. This is all real features. So you see this from absorption to emission. So this needs to be explained. I'm giving a hint here that our models are line-by-line radiative transfer models, so we can and we will and we do simulate the oxygen bands in a high accuracy, and we always have to compare and be careful with what observational resolution you observe to interpret the strength of this band correctly. High resolution has quite some promise. As you can see here, these are observations actually this time with the William Herschel telescope with some higher resolution in the oxygen A band, and some first simulations with clear sky and with aerosols. So you see the impact of aerosols and we are pretty sure that we can actually retrieve aerosol and cloud parameters through these measurements on a more global scale, which may be interesting also on the climate scale. So concluding, I think, with the outlook towards what we believe is one of the strong techniques now in getting towards biomarkers, and in particular oxygen biomarkers in exoplanets, is actually, in this case, transmission spectroscopy, but focusing on the oxygen A or B band. And simulations are ongoing that you may need an ELT. The techniques as was already done in the first day of this conference, is now being established that you do need cross-correlation techniques in these bands to distinguish the telluric and the planet contribution. And if you do this for oxygen, you can do this. The disadvantage is a little bit, I don't know if you see this, depending on the spectral type, these are still many orbits that you need. I think this coincides with what has been said before. Maybe for the M stars, these are 4 years. This is not out of feasibility, but a really interesting case is now Prox-B, as you know, M star, the nearest M star which hold a planet in the habitable zone. So people now with the VLT are seriously thinking in combining high spatial resolution and high spectral resolution instruments. And again, the simulations go in this case on O2B. Band, and so this is something like 60 nights with the VLT, probably something that you may want to expect. And I conclude with I hope that I could convey that spectropolarimetry of planet Earth is an interesting technique.
Oh, thank you very much for a very interesting talk.